when you start to apply some current, what you're doing is actually you're tilting this washboard. And you tilt it and tilt it. Still, you see, your particle is stuck. And at some point, however, it starts to roll down. You see? So it's, at some point, it starts to roll down. That's your critical current. Okay, what is a Josephson junction? Is you have two superconductors that are coupled with each other through some form of a weak link, medium barrier, whatever you call it. And the important thing is that the two wave functions can overlap and yield a single valued current phase relation, right? We come back to that again later. So this gives you a way to control the phase difference between these two condensates, so you know where and how this phase variation is going to happen. Because as I said, the condensate amplitude drops, so if you're passing a current, because the current needs to be continuous, then what you need is to basically compensate for this drop in condensate with higher, phase gradient. So Cooper pairs have to go faster. If there's not enough Cooper pair, but you need to match the same current, the Cooper pairs that have to basically go faster. And that means this is where all the phase variation happens. Hey. Okay, and then we quickly covered that there's, we have Josephson junctions. They give you this Fraunhofer pattern, and they're kind of equivalent to this, single slit diffraction pattern. Now, if you connect two Josephson junctions together, this is called a superconducting quantum interference device, or a SQUID. And you get a double-slit interference pattern. These are extremely sensitive tools for measuring magnetic field and other things, basically current, magnetic field, temperature, microwaves. They're very versatile and very accurate. Yes, there was a question.
Does the optical equivalency go even further? Is there like optical equivalent of like a diffraction grating or a Fresnel lens?
Pretty much, yes. So we have to see, but it depends on. Yeah, look, in many ways, you're still dealing with waves here, right? Yeah. And it's just that instead of spatial, space on the screen varying the wave fronts and forming interference, here now replace space with flux, magnetic flux, for instance, or other things that could vary your phase, and you're going to end up with the same physics. So
you could do some like equivalent of Fourier optics.
Yeah. Yeah, we do that. Actually, I'm going to show you a couple of examples later. Good. So now going back to Josephson junctions, in general, the reason that why there is now, I dedicate literally a weekend, 1.5 lecture, which is basically a quarter of this course to Josephson junctions, is because they're super important both in terms of applications. So if you think about it, Josephson junctions are what transistors are to semiconductors. Josephson junctions are to superconducting technologies or quantum technologies what transistors are to normal, semiconductor technology. They're just as important. And if you think about qubits, if you think about quantum sensing, all of these, one way or another, they're using Josephson effect and Josephson junctions. So in terms of applications, anything that becomes, we're talking about anything that's not optics, let's say, okay, there's forum, but anything that is not optics is going to be relying on Josephson junctions when it comes to qubit chips or quantum sensing. But they're also super important for, in terms of fundamental physics you can do with it. As I said, you could use the properties of the weak link to modify, to engineer the wave function of the superconductor. So instead of just relying on the, you could basically start with the boring wave function of a S-wave superconductor like niobium and use the properties of this weak link to create pretty much whatever, symmetry you want. You could go chiral, you could go P-wave, you could go triplet, you could create Majorana modes and so on. So there is a lot of rich physics that comes out of just this proximity effect and using, you know, the properties of these weaklings. You could use topological materials and so on. So now, going back to junctions, as I said, there is many types of barriers, any types of weaklings you could use. The most prevalent one in industries, like if you look at Google, you know, Microsoft, Intel, whenever they basically they make qubit chips, or if you look at industrialized sensors, like or SQUID amplifiers, these things, they use SIS junctions. That means that there's two superconductors that are separated by an insulating barrier. Why? Well, because I think part of it is because it's historic. I don't know. I think the industry is just afraid of change sometimes because they have their pros and cons, and sometimes, well, they can also be mass-produced pretty easily, but it also doesn't mean that they're the best for qubits, but somehow we're stuck with them. They're easy to make, anyway. So that's the SIS junction, but it could also be a normal metal. So it actually took a few years, or actually maybe a decade or so, before people realized that you don't need to have a tunnel barrier. You actually, so a tunnel barrier, any idea what the thickness of a tunnel barrier needs to be for these two superconductors to overlap? And 1 nanometer. Okay, more or less? Okay, great. Yes, it has to be less than a nanometer. So normally it's about 3 angstroms. Yeah. So that's it. But what about a normal metal? Yeah, it could be hundreds or it could be microns even. Right. So, but the point is, it could even be a superconducting constriction. But the important thing is that actually, well, all that matters is this current phase relation. But meaning that for how much phase difference, you get how much current through the junction. And this is, you know, goes back to this first Josephson equation, right? Shown here, that supercurrent varies as a sinusoidal relationship with the phase difference, phi. And IC is basically the maximum, it's your junction's capacity for supercurrent transport. It can't exceed that. So that could deviate from this sinusoidal relationship, and we're going to see some examples later. But what is important is that this function remains single-valued. That means that for a given phase difference, there is a certain supercurrent through your junction. So in this curve, F will not qualify as a Josephson junction, right? That would just be a bad superconductor with a defect, basically. Right, so now we come to the hardcore stuff. We talked about how you could basically use this. There's a current phase relation. That's the first Josephson equation. Then there's a second one, which is just as important. It's called the voltage phase equation. So first one is the current phase relation. This is the voltage phase relation. And this is important because unlike in, you know, if you have just a piece of superconductor and you do something to it, you pass the current through it, the moment you get a voltage, that means you've exited the superconducting phase. There is all the interesting stuff are gone. So you see a voltage, if you get a piece of wire, pass current through it, but the moment you see a voltage, that means all the interesting physics is gone. There's no quantum coherence, there's no quantum transport. But in Josephson junction, that's a different story. Here, your voltage is actually coupled to the Josephson energy and your Josephson transport. So you have quite a while, if this is, let's say, current voltage curve, there's quite a while till it becomes fully linear. And during this regime, you could use the voltage. You could use this voltage phase relation. And now, well, based with these two, you just can do a simple derivation, and you can derive the Josephson energy and the Josephson potential. And we talked about what this looks like. Today, I've actually brought props here. This is a little thing I made, well, I asked FMD to make. It doesn't always do what I want it to do, but it somehow apparently helps. So think about this. Suppose you have we already covered in the slides, but let's say this is the phase of your junction. This is your phase particle in this washboard model. So I'm just going to put it in there, right? Here. Now, normally it's sitting somewhere. Where? Well, usually at 0. So there is 0 phase difference, and this is where it's sitting. I mean, it's a periodic function. It's infinitely periodic, so forget about that. So your phase particle is sitting there. Now, it could basically, I don't know, could be rocking back and forth a bit, but at the end of the day, if you think about the time derivative of your phase, or your phase velocity, it averages to 0. So your time average phase velocity, normally, if this is just sitting there in its ground state, it's 0, right? But when you start to apply some current, what you're doing is actually you're tilting this washboard. And you tilt it and tilt it. Still, you see, your particle is stuck. And at some point, however, it starts to roll down. You see? So at some point, it starts to roll down. That's your critical current. Okay? So the moment where your phase starts to roll down this washboard is the moment that you've developed a voltage. But so in this analogy, you can think of as phase as the position on this washboard, right? And because it's a periodic function, you don't really need to, all you care about is one period, where it is. And in that case, then the velocity is your voltage. So the faster this one goes, the higher the voltage. And that's why when you increase the bias current, your voltage keeps going up. And it goes up and up until a point where this becomes basically a free fall. It would be like this. At this point, you're not really feeling all this corrugation, all these features on your washboard. So here, at this point, your phase particle doesn't care about your current phase relation anymore, or your Josephson potential. So far clear? Good. So this is just a visual representation of it, but this washboard potential model actually becomes more useful when you put it in the context of the RCSJ model. This is the so-called resistively and capacitively shunted junctions. So what it does is it's actually you basically take your Josephson junction and you treat it like a classical electronic circuit, with one exception, and that is that you also now have a superconducting channel. So this would be the circuit diagram of a junction. Don't forget. So it doesn't mean that there is a capacitor or a voltage attached to your junction. No. Here, we're talking about just the junction, and this is the way it's represented in the RCSJ model. Okay? So it's a model. It's not actually that we're attaching resistors or capacitors to your junction. Why? Because your junction, the weak link material of the junction already has those. So the weak link of the junction has a finite resistance, right, and capacitance. So, for instance, if you have a tunnel junction that's made out of an oxide barrier, the dielectric material, you're going to have high capacitance. So there, capacitance is important. But if you have a SNS, it's like your weak link is a copper film, There, you have no capacitance because there is no dielectric material. You can ignore it, right? So these are real properties of the weak link of your junction, right? So the R and the C correspond to resistance and capacitance of your junction, and they're connected in parallel to the superconducting channel. So when you're biasing, when you try to put a current through your Josephson junction, this is the circuit you need to think about, right? Now, when we are below the critical current, so you apply current, but you're still below the critical current, we can ignore this R and a C. Why? Yeah, the superconducting channel shorts everything, right? So here, there is no voltage. Therefore, these guys don't matter. Everything is just shorted by this superconducting channel. Okay? Now, what happens then is that, wait a minute, what happens when you go above the critical current? Well, this is where things get a bit more interesting, because now you've developed a voltage, right? You now have a voltage across this circuit, and this is a time-dependent voltage. Because if you remember, voltage was the time derivative of the phase, okay? So now you have 3 transport channels in this diagram, right? I mean, in reality, it's just one junction, but there's 3 things going on in principle. One, you have basically 3 channels. One is your supercurrent. This is a current that goes through this, your superconducting current. So even when you have voltage, you still have your Cooper pairs. It's not like they go away. You still have all your supercurrent. They're there. They're being transported, right? So that is the superconducting channel. But then there is 2 normal channels of unpaired electrons. So this is basically going in addition. It's like a parallel channel in addition to this of electrons. So there's unpaired electrons are also being, transported. And this is what you write the current for each case. So you have now in the resistance case, this is your normal current, and this is the other one. But for the most part, you don't actually, you don't need to worry about this normal current, because again, until you go to the phase state where everything becomes linear and ohmic, your supercurrents are going to dominate your transport. So, is it so far okay? So you have a time-dependent voltage, right? That comes from your phase particle going down, and that means that you have a time-dependent phase, and that leads to what? A time-dependent current. So this supercurrent is not just, you're above in the voltage regime, you're not just applying a DC current, there's also an AC current, because the phase variation is determined by the phase, which is no longer constant. So your phase, as I said, if this guy keeps going down here, you see, and your current is the sine of this phase, you see, your phase is constantly going. This leads to an AC current. Yes?
Is the phase dependent on geometry, or is it?
We'll come to that. You mean phase variation? No, normally not. Like when you're applying bias, no, this is just you dealing with at a given case, you're only dealing with your washboard potential. But the stuff about geometry, so we'll come to that later. So if you now apply just simple circuit calculation, Kirchhoff's law, and so on, this is what you're going to get. This basically the equation that determines your how your phase derivative, capacitance, resistance couples into your supercurrent transport, which is again a function of your Josephson potential. So the derivation, like basically, you're going literally from what your Josephson potential was with respect to phase, and now here you're just replacing, for instance, this phase derivative with the expression for voltage. It's just simple undergraduate maths, right? So, but this is basically the so-called RCSJ, the differential equation for the RCSJ. Now, where have you seen this type of equation before?
Is it done harmonic oscillation or something?
Yeah, it's exactly that. So there is a very, again, a simple classical equivalent to this case. So basically, you're thinking about here, even though you're dealing with quantum transport, and you see, the type of weird stuff that can come out of it. The actual equation that you need to model this system is a harmonic oscillator. Yeah. And in this analogy, the phase, again, we went through it, is position, voltage is velocity. Now the difference is now that there's also, if you have capacitance, that'd be like mass. So if I have so it's a question of whether I use this coin or this coin, right? Smaller coin or a bigger coin. That basically, this would be high capacitance, this would be low capacitance. And in that case, friction, this is the only thing that you need to kind of flip your way of thinking. Friction is the inverse of resistance. So friction is actually conductance, right? But, we can live with that, right? So I know in your head you think resistance, friction, but it's actually the inverse of that. Other than that, you could use this model to actually understand your junctions and think about your junctions. I think it's a very useful, intuitive way of looking at Josephson transport. So this is the RCSJ model. It's actually extremely, useful because, for instance, even for when we're working with SQUIDs, then in that case, you just extend it to 2 channels. So you have 2. This is the model you can use. I mean, in this case, some cases, for instance, you can ignore the capacitance altogether. So here's an example of a SQUID that Matthias made when he was a master's student. So what you're looking at is a superconductor, molybdenum germanium, and he basically goes in with the focus ion beam, cut away these parts. So first shapes the ring, and then he goes and cuts away this part. So now there is under this molybdenum germanium layer, actually you don't see it anywhere else, but there's a layer of silver, and silver is a normal metal. So in this case, when he makes a cut, he makes a very, very tiny normal metal weak link here. And you could use RCSJ not to just explain, okay, what happens to critical current. You could really fit your entire current voltage characteristics and even take into account different types of noise, that exists. So you can get a very nice, accurate fit that would give you all the characteristics of your junction. What is your normal state resistance? If you have capacitance, what is this capacitance? What's your critical current? And how much noise you have. So in a way, it's a very powerful technique. And recently, actually, I didn't even know you could do this, but Matthias' student, Wessel, basically started applying neural networks and machine learning to doing RCSJ simulations. And what I'm showing you is actually one of them. I also forget which one. One of them is an actual measurement, the other one is a simulation. And I mean, for me, this is very impressive because people who can do, let's say, RCSJ calculations properly, most of the time people, they just kind of butcher it, or, But people, I don't know, groups that can do this properly, I can probably count them on, with my fingers. But that still takes, let's say, a few days, to figure that out and just model that thing. And this entire simulation with the noise, with everything, is done in less than 5 minutes with neural networks. So, oh yeah, this one was the simulated one. That's the measured one. Okay. So you can actually, this is extremely useful, for, and it's actually, instead of cherry picking part of your data, instead of just looking at part of it, you're simulating the entire interference pattern. So maybe I didn't explain, but these are basically, we're talking about hundreds of current voltage measurements taken at different fields, and you have this basically, what you're seeing here is this, the double-slit interference pattern. But you see that there's not exactly like the textbook. Why? Because, for instance, if you have asymmetry in your weak links or in the, path that the current takes, your inductance or so, that would change your pattern from the textbook, double-slit interference pattern. But those are things that you could easily simulate. Yes?
How long did you say does it take to measure this graph?
This really depends on, well, there is, I think in this case, it's done in a very slow setup, so this is probably 5-6 hours. But you could also, if you optimize your electronics, you could do it literally in half an hour, maybe even shorter, yeah.
Theoretically?
No.
Practically?
Practically, yes. So, but proper electronics, you can literally take, there's way better ways to do this stuff quickly, and well, we could talk about that, but it's an electronic thing.
Okay.
Yeah. Good. Yes?
Just looking at the graph earlier on the tilted washboard potential, you said that as soon as you surpass the critical current, you develop a voltage.
Yes.
Here the critical current, it says it's at 25 microamps.
Yeah.
Develop a voltage before that.
Yes, that's a very good point. Yes, you do develop it because this actual critical current, if it was in the right electronic, if the electronic setup was properly filtered and we didn't have thermal noise, this would be flat up to here and it would jump up. This rounding you see is because of lack of filtering in the electronics. Maybe I'll say a few words about that later. But basically, rounding is due to telecommunication, mobile phones, all this stuff going in and coupling with your Josephson junction, and that gives you this rounding, right? But not if you have a good setup, you don't have it, but here you do have it because of that. Good. You can use this washboard potential to make sense of your current voltage characteristics. Very simply. You don't even need to do this modeling and all these simulations, actually. Just by looking at your current voltage, it tells you something. So here, what I'm showing you is a current voltage of a Josephson junction. As you see, there's a critical current where you develop a voltage, right? Then we go up. And then we ramp down the current, and you see there's a bit of a hysteresis now. So it's not just dropping down at the critical current, it's actually going down at a lower current. Any idea why that could be?
Because you're going up the washboard.
Well, no, you don't never go up unless. So what you do with the current is to tilt it down. And this is the problem. But you see, once this particle gains some momentum, right, it's not just going to immediately stop, right? So this is called a retrapping current. So there's a critical current, but then there's a retrapping current. And, oh, did I drop my coin again? Oh, there it is. Yes. So this particle, if it's massive, for instance, then you're going to basically, you need to tilt it, and once it escapes and gains some momentum, then bringing it back again, you need to go even further back for it to be go back to the zero, to trap it in one of these wells. So now, what does it mean if a particle is massive? It's capacitance. Or, okay, so this is, by the way, this is one way to look at it. So this is called, the term for this type of junction is an underdamped junction. When there's a big hysteresis between the critical current and retrapping current, we call this an underdamped junction. And you could also have overdamped junction. So this is an example of an overdamped junction where you see this is actually, you can't tell them apart. This is a critical current going up and down. You only see one curve basically, right? So there's no hysteresis now between a forward and reverse sweep. This is called the overdamped junction. Now you could think of this almost like as if, instead of this plastic on my washboard, suppose I dropped it again. Suppose I put a sticky tape or make my washboard sticky. If my washboard was, sticky, then it would also not have, it would also just stop the coin right when you need it, like right when you go back to your critical current. But if it's slippery, let's say this is the underdamped case, then, well, yeah, you're going to have to work harder to trap it again in one of these minima. Does it make sense?
Does that tie then to the conductance? No.
Yes, it does.
Okay.
So it's a combination of both. So the things that are important is capacitance or not, whether you have a massive particle or not, and also conductance is important. So high conductance, in a way, basically that you can treat like friction also. But it's all of those things. So it's a combination of how massive this particle is, how sticky this potential is, and more important, also very important, how bumpy this washboard potential is, right? If you only have a washboard potential that is just, if it's, let's say the barrier between each minima is how tall that is. That also plays a role. So, but you can basically get some guidelines, so you can keep in mind some guidelines. So here, actually what I'm showing you is two different types of junctions. One is, again, niobium gold bilayer, where they now etch away this gold part. So you have now 1.8 microns of gold. So this works like a SNS junction, right? And in this case, you have a multilayer of niobium, aluminium oxide, niobium. Okay? So, which is a SIS junction. So I said that this is the most common type of junctions used, historically and also nowadays is the SIS junction. It's because of this aluminium oxide. So if you deposit aluminium, if you have a thin film of aluminium, you could deposit it in an ultra-high vacuum chamber, and then you put in some oxygen. It actually has a self-limiting oxide. It forms a 3 angstrom layer of oxide. And that is the insulating barrier. So in a way, because it has a very well-defined thickness, it's easy to make thousands of these. Just put some oxygen, you form the barrier everywhere, and then you put the other layers on top. So in this case, you put some aluminium. So first deposit the niobium, then put the aluminium, letting some oxygen, form this oxide barrier, and then put the niobium on top. So now you've created a tunnel barrier. There's a thin metallic layer also in there, but we can ignore that for most of it, because a lot of it is just going to be, your Josephson junction is predominantly defined by this oxide barrier. And so now the question is, which of these two junctions will have a larger hysteresis, you think? This one or this one?
Top larger.
So which one, say? Would have larger hysteresis? Because?
There is a big capacitor in there.
Where's the capacitor?
Between golds.
Between the gold?
Yeah.
But between the gold is nothing.
Oh, there's free space.
Yeah, but that's not your junction. So when we're talking about capacitance, we're talking about capacitance of your weak link material, not just capacitance everywhere else in your junctions. Yes? Yeah?
Maybe that's all because you have the lower resistance.
And
But because it's the inverse of the resistance, so if it's lower, then it's higher.
lower resistance. Okay, okay, that's also right. I mean, in a way, you could be right, but in this case, you're not. I mean, actually, SNS junction. So the difference in resistance is really having a high capacitance is way more problematic in this case. So SIS junctions, the big problem they have is this huge hysteresis. And so having a massive particle with a lot of momentum, stopping that, retrapping that, is always, that's a bigger problem. But if you were to compare two SNS junctions where there is no resistance, then you're right, the one, with the higher conductance is probably more likely to see it. But normally, SNS junctions, they fall into the category of overdamped junctions anyway. So they're normally they don't show hysteresis. Okay. So let's go back to the dynamic regime again. So here, let's go back to this washboard potential. Because we said that, okay, when you enter the regime where you pass your critical current, there is now an AC element in your circuit. So the transport, you have an AC transport, right? Remember that? It was 2 slides ago. Good. Very good. And with that, basically that means, so if you have you could now determine the frequency of your Josephson junction. So this grows with voltage. As I said, the higher the voltage, the faster your particle is going, right, on this washboard potential. So if I, tilt it more voltage, particle goes faster, and that means higher frequency. So you can basically, there is a intrinsic Josephson frequency that grows per voltage. So if you're depending on how much voltage you get out of your junction before it becomes completely linear and boring, within that regime, your transport is modulated by, on the time scale of a certain frequency, and this is the Josephson frequency. So it's 483 gigahertz per millivolt. That means if I have 1 millivolt, if I'm measuring 1 millivolt here, this frequency is going to be 483 gigahertz. Okay? But the important thing is now, you should remember that whenever there is a oscillating transport, if you have, charged particles that are now they're not DC, that's going to produce an AC field. It's going to produce EM fields, right? You pass a current through a wire. If it's AC, you're going to get radiation out, right? So what this means is, this is a very key point about Josephson junction, is that basically you can apply a DC current, just from a battery, whatever, just bias your Josephson junction, and you convert that to high frequencies. So you can go from a DC to high frequencies, radio frequencies, very easily, just based on this voltage. So what frequency range? Well, it depends where you stop. If you bias it here, if you bias it basically at, 1 microamp, this is going to be 1 microvolt is going to be 0.4 gigahertz. If you stop at nano, it's going to be megahertz. So you could basically go anywhere. You could produce anything from megahertz all the way to terahertz by just tuning what current to apply to these Josephson junctions. That's a huge range. So this is very attractive for a lot of applications because normally you can only produce a very limited frequency range, right? And the ability to go from DC, direct current, to such high frequencies, that is, that you can't find any equivalent to that. So this is extremely, in a sense, useful of up converting low frequencies to whatever frequency, high frequency you want. And this is particularly important when you go to a so-called, terahertz regime, because there is a thing called the terahertz gap. You probably never heard of this, have you? Yeah, so terahertz actually radiations, they're very useful for a lot of things. I'll show you an application in a second. But the problem is that unlike microwaves, gigahertz, megahertz, producing terahertz frequencies is extremely difficult. And here, you could do it with Josephson junctions. What kind of junction? Well, you could make one, but there is a certain type of junction that is actually, it happens intrinsically in a family of superconductors, the cuprates. So as I said, there is, when we talked about pairing symmetries, there is this family called cuprate superconductors. They're defined by these copper oxide planes. Now, if you remember, these copper oxide planes is actually, they're the superconducting sheets, but they're separated by a few angstroms. And that means that it actually, if you apply current along the c-axis of this crystal, so you just get a crystal and apply current through the c-axis, what you will have is an array of thousands of Josephson junctions. And these are highly synchronized. They're very coupled with each other because this is happening, you're basically putting in thousands of junctions that are strongly coupled because of the crystal, the way it is. So this is a kind of a built-in array of thousands of junctions with same coupling, same capacitance, same resistance, repeating themselves, and that gives you huge output. So here you could go to millivolts regime pretty easily because there's now thousands of these junctions, so their signals add up. And in that case, you could use these for generating terahertz radiation. And here's an example where they do that. So they're basically using these cuprates to generate a beam of half a terahertz, right? And then this is the image they get. So this beam, if you shine it now on this is a photo of 2 coins in a paper envelope. This is the pattern you get from that beam. So this, by the way, these fringes you see is because of the interference between the 2 sides of the paper in the envelope. So it's already something that you can actually do for, scanning, detection, that sort of thing. The funny thing is that actually people really tried, it took them a while to get this radiation, detect this radiation. Why? Because it was extremely sharp. So the emission peak, the transmission peak, the peak that corresponds to this, high frequencies, this was so sharp that a lot of studies, they could just not resolve it. We're talking about you're in a terahertz regime, but your peak is only 1 hertz. So it won't even show up on your monitor unless if you really dig in and zoom in, and then you're like, oh shit, there's a sharp peak over here. So why? Because this is a very highly synchronized system and gives you a very sharp resonance. Okay, so this was just a fun application of this, where basically we said that you send in DC current, you get radio frequencies out. But what about the reverse? Because the reverse could also happen. What do I mean? Well, this is something called Shapiro steps. Now, the way you do this, so if, for instance, you make a device, and you want to know if it's a Josephson junction or not, back in my days, when I was, junior PhD, we had to take those long-ass, magnetic interference patterns that would take overnight, and even then you can't make sense of it, and then you don't know, is it a junction, is it not a junction? That was a whole debate. Now, there's a very simple, very elegant way of doing it that would tell you if it's a junction or not in literally, 5 minutes. What is it? It's simple. It's just you put a basically, this is a radio frequency cable. It's called a semi-rigid. You put an open-ended coaxial cable right above your sample. And then you just send in some microwaves there. You're kind of spraying everywhere, including your sample, with radio frequencies, right? Gigahertz or whatever. And what you will find here now is suddenly these quantized steps in your IVs. And this is kind of, it's a very simple experiment, but you get very beautiful results out of it because you see, this is for different, I'm showing you basically IV curve for different powers. But what you have here is that you see, that regardless of the power, and also regardless of the junction, what you're going to get is the same quantized steps, and they're in the units of frequency times phi naught, or h over 2e. So h over 2e, universal constant, right? The only thing you need to know is the frequency. So if I put in 1 gigahertz exactly, I'm going to get basically, so it would be 1 times 10 power of 9, and you times that by phi naught, which is 2 something, 2.0 something, to minus 15. That means I'm going to measure exactly 2 microvolt. So these steps happen because of this Josephson radiation. Now, what is going on here? Why do you see these steps? Now here I'm going to take out my props, and this is, I wish there was a better way to really visualize this, but bear with me, right? And after this, we're going to take a short break. So, as I said, when you're tilting it with a DC, you apply a DC bias, you're tilting this washboard potential, right? Now, what do you think an AC current will do? Because this microwave radiation, what it's effectively doing is that it couples to your junction's dynamics. So what it does is that it induces an AC current in your junction. So before we were talking about going to voltage regime and producing AC current, but now you kind of driving your junction with an AC current. So what would that look like? It would be like this. It would be like I did this. So when I'm here, this is what I'm doing, right? Let's say all the way to, if let's take this curve, the purple, I don't know, whatever. What do you call this color? I don't know, green-ish?
Gray.
Okay, I'm getting different now. So, okay, right.
You're pointing at like 4 colors.
That one now.
That's green.
Okay. Yeah, that's the one, the 16 dB one. So you see, up to 10 microamp, I'm doing this, and I'm gently moving, and at the same time applying a DC bias. So there is a gentle rocking back and forth, rocking back and forth. And then at some point, unfortunately, this is where my coin and my wash potential fails me. You get your coin escapes, goes to the next minimum, but it stopped because this thing, if I do it at the right frequency, unfortunately, I'm not that talented. Basically, it means that the particle only steps one minimum down. So you're going from 0 to the next period, and it gets trapped there, right? That, again, but when it gets trapped again, remember, what was voltage? Voltage was the time derivative of your phase, right? So I want you to understand why these steps happen, because voltage is your phase velocity. And with this AC current, you're now putting it in quantized units. Why? Because the first steps means that your phase particle is skipping only one minimum, going here. So you're coupling it here, and therefore you're stopping it the next one. At that point, your phase is jumping by 2 pi, right? From one minimum to the next one. That means a shift of 2 pi per period, and the period is basically this, the time constant here is this 1 over frequency. So the frequency is 1 over time, and the distance in this case is 2 pi in phase space. And 2 pi in phase space means winding your phase by exactly what? Phi naught, h over 2e. So when you skip one minimum and you go to the next one, in the first steps, you know exactly what your velocity is, because it's exactly how much phase travels in that time scale determined by your frequency. All good? Now, if you push it further, you can skip this minima and actually jump 2 minima down. In that case, you get the second step. So you have the second step now, which means that within one cycle, one time period determined by your frequency, you've now skipped. You change your phase by 4 pi. 2 phi naughts, basically, right? So as long as you remember that velocity, in this case, voltage is your velocity, and velocity means distance, which in this case in phase space would be 2 pi or multiples of phi naught, and your frequency, which is the time scale, you can actually determine, you can see why these voltage values come in quantized units, because you're skipping one step, you're skipping 2 steps, you're skipping 3, 4, 5, 6, until they go away, right? That is Shapiro step, and actually, they are extremely accurate. They're in fact used as so the thing here, I want to say that this step height is extremely accurate, because actually it's used for to define what 1 volt is. So the standard unit of voltage is determined using Josephson junctions. Why? Because we know we can get frequency, we can have radiations to be super ultra accurate. I don't know how they do it, but you can imagine the error bars on giving us, determining the energy of a photon that comes out is very, very small, so they can be very, very precise with the frequency. Then your Josephson junction basically is just going to be, the error bar is just going to be determined by the error bar on this radiation. So you're getting a voltage out of your frequency of your photons. So if you have a very accurate, source that gives you a fixed frequency, then you can use that to determine what exactly 1 volt is. So this is basically what they do. They have an array of, I think, 10,000 Josephson junctions here that are ultra coherent, and you spray them with these microwaves and determine exactly what 1 volt should be. Yeah.
Okay, so first time we jump once and then you jump twice. So why from 1 don't we go to 3 and we go to 2? You know, like first time we jump to 1 quanta.
Yeah?
And then from
Why would you go
if
3?
we jump twice, we go to 3.
Why would you get to 3?
Because we jump twice to 4 pi.
No, but where is your reference? You either, it's a periodic, infinitely periodic washboard. It doesn't matter. I mean, as long as, maybe I don't understand the question. Why would you go from 1 to 3? It's not that you've already, okay, I see where it goes wrong. You're thinking in a bit as if there's 1 particle and 1 potential picture, and you say, I've already jumped 1, and now I'm going to jump the next one, let's say the 2 steps. No. We're talking about literally, it's a periodic function. It doesn't matter where the original minima was. So when you're measuring 1 step, that means your particles, think about an infinitely long washboard with infinite particles in it, right? There is no fixed reference point. In that case, you either skipping 1 minima to the left and getting trapped there continuously. So this is happening all the time. It's not that it happens once and that's it. Because if it happened once, then your voltage would go to 0. It would just, but you're getting a voltage continuously. This step is a fixed step until you tilt it more, and then your velocity is higher because you're now skipping 2 minima over that 1 cycle where the washboard is pushed back again. Is that clear? Okay. But it gets even prettier, of course, when you sweep the power. As I said, the power makes these steps wider and wider, and this is the kind of patterns you can see. So this blue part is where your voltage, where you have the steps. And so you could plot it as dV/dy, or if you want to look at the quantized units, you look at dI/dV, and you get these streaks here. And notice that there's a little bump here that actually this is so your first critical current. This is your, this regime, this first regime where you don't have any steps. You see, it actually goes away halfway. Any idea what's happening here? So imagine you're increasing power, you're shaking. You don't change the frequency, but you're shaking your washboard, more violently. And at some point, and DC bias is just tilting it, but at some point, the amplitude of this AC, you're shaking it violently, it actually is larger than your critical current. So your particles are going backwards. So there's a crossover from particles going downhill to particles going uphill. In this case.
But then it happens again at higher, and that's also repetitive.
It's then you switch directions. So here you're still getting the steps in both directions, but now for a larger amplitude of AC. So it's in one, you should only look at it, this is the direction of DC bias. So when you're looking at here, you're still going to get the steps, but these are, I think it takes some time to see it, but basically at this point, it's not super important, but it's a point where your particles now going backward because your AC is larger than the DC that you apply. Okay. Yeah, of course.
Yeah.
So, no, you just got here. So I want to move on to the interference patterns, which we briefly mentioned, but didn't really discuss why you get this so-called, for instance, Fraunhofer pattern. So the reason you get it, as I said, it has to do with 2 things. It's you got to be careful. There's an absolute critical current that's determined by the material properties and temperature and so on of your junction. So that's the maximum supercurrent you can actually put through your junction. But then when you're doing a measurement, there is a critical current that you measure. So this is the part that in your measurement you see that there's a jump in the voltage state. But there is, what you should think about it is that there is now, imagine your junction being this cup of coffee now. If it's empty, you could pour coffee to it all the way to the rim till it starts to spill out. When the moment spills out, that's the moment you reach your critical current. But if there's already some coffee in there, you can only put less coffee, right? So you get here, the maximum you see here corresponds to the point where your cup is empty, right? So you can pass maximum supercurrent through it. Now, when you apply a field, what happens is that, well, it introduces, you apply flux to superconductor, that results in phase. So you introduce a phase offset. You produce, same thing with little parts and everything you've seen so far, right? Magnetic flux introduces phase. And now, what does that excite? What does that introduce? No, when you apply flux to a condensate, what does it do to current? Yeah, phase variation results in current, right? We're not talking about voltage here. We're just talking about, in this case, you can actually forget the voltage part on this slide for now, at least, right? So when there is a magnetic flux, there is a phase offset that is not, so your phase is not zero, so you're actually adding. Now, the thing is, think about it this way. This phase is created, the flux introducing a phase now. This phase needs to be compensated by supercurrent. But there's a, and that's going to be adding, it's just filling up your cup with coffee. So your critical current starts to go down. The thing you measure, you reach your maximum capacity sooner. Is that clear? So when you apply a flux, you're changing the phase. And now, question, this phase, however, so this phase is proportional to the area of your junction. So as I said, field is really not the unit you should be looking at, it's the magnetic flux you should be looking at, right? Field is just flux divided by area. So the period here, of course, in the measurement, you're just applying field, but what really matters here, it's the periodicity of your Fraunhofer pattern or so on, is determined in units of flux. And the flux then, as I said, depends on the area of your junction, right? How much. So what would be the area in this case? So this is the equation that I'm not going to derive it, but this is the equation you would get for critical current as a function of magnetic flux. So the flux, this is the equation that goes from area times field, gives you the flux. So you can plug it in, and you get this Fraunhofer formula. Now, what I want you to tell me is that what is this area for this junction? Here, I'm giving you the dimensions, WL. Well, what's going to be the area of my junction? The yellow part. So that would be L times W. Is that right? Think about length scales for phase. How quickly can phase vary in superconductors? Because suppose if it's a tunnel junction, your area is just going to be 3 angstrom by that logic. But think about it, the yellow part is not telling you about the phase. The yellow part is telling you about where the amplitude of your condensate drops. And the length scale for the amplitude what's the superconducting length scale that characterizes the variation amplitude? Coherence length, yes. psi. Now, what about the phase? Can phase just drop quickly from one place to another? No, it can't. It has to wind continuously over a characteristic length. What is that characteristic length? Think about what happens when you put stuff in magnetic field. What was the characteristic length for, yes? Yeah, lambda, penetration depth. That is the length scale over which your phase varies. So your effective area is actually not this tiny trench, because this is just where the amplitude of the condenser goes down. The effective area is this L plus 2 lambda. And this lambda is not, you know, for thin films can even be much larger than the textbook values. But what you should remember is that there is the size of a barrier. That's one thing. But then there is the magnetic length of your junction, right? Because the size here is basically related to the amplitude of condensate, but the magnetic length is the length scale over which your phase can actually wind. So that means that if you start here, you go here, you here, complete the, you know, do a full loop anywhere within this region, you need to wind by multiples of 2 pi. Your orbital phase needs to wind by multiples of 2 pi. And it has to basically, so your phase needs to, you know, spill over a bit over the length scale of lambda here and lambda there. So the size of your magnetic length scale is actually related to lambda, which is also, you know, a bit temperature dependent. So keep that in mind. That's clear so far? Okay. Now, let's, you know, think about what is actually happening, why you get this pattern, how to basically analyze this pattern. So start at 0 bias. In this case, what this red line is showing basically is the phase variation across the junction. You see, your phase is uniform. You know, you can apply current, it will just uniformly change depending on how much you bias it with. But because there is no field, there's, you know, it's just going to be the maximum value of your current. Because there is no, you see, your cup is empty, you can fill it to the rim, and this is why you get maximum IC here. Now you apply some magnetic flux. This is your phase. Suddenly you now actually have a bit of your phase variation in your junction starts to vary as a function of space. So now why? Because there is a screening current. It's a little bit, I know, you know, here unfortunately it's a phase, but bear with me, because what you actually have is that there is supercurrents now going in your junctions around, you know, to counteract magnetic flux. Now, at this point where you hit the 0, right, when your critical current reaches its minimum, you've reached exactly unit of 1 phi naught. So basically you have a vortex here. This is called a Josephson vortex. And it doesn't have to have a normal core, right, in this case. So in this case, why? Because basically what is happening here, I mean, if we ignore that for now, what is happening here is that there is the field introduces current, the circulating current that go here up and down. And now when you add more current, well, it's like a full cup. At this point, you flooded your system with a lot of supercurrent that are generated by the flux, by just, you know, screening the flux to be in units of phi naught. So in this case, you have 1 phi naught of flux. You have maximum field-induced current running through your junction, so your cup is full. And in that case, you pour a little bit more coffee in there, you put a little bit more bias current in there, it spills over. That's why you have a minimum in your critical current. But then you increase the field further, right? In this case, you compensate for some of that. Your supercurrent the field-induced supercurrent is actually less. So the phase variations is less, so you could push more critical current, more supercurrent through your junction. So remember the first lecture when we talked about little Parkes experiment, how, you know, the current, its job is to arrive at 2 pi phase, right, when you go around in a loop. So in this case, this is your loop, and you have currents generated by this flux that doesn't add up to, you know, that's generated by this phase shift. And now if you start to compensate for some of that, then you actually have room now to push more current through your circuit. This, you know, I mean, it's, you can look up this book, Applied Superconductivity. It's actually online. It goes through it in more detail, but this is as far as I want to go because there is more interesting stuff. Now, one thing is that, of course, you know, a lot of times you do get this nice Fraunhofer pattern. This is the standard case. This is one of our own junctions. This was a, SNS type of junction. You get a Fraunhofer pattern. Note that actually the first lobe is twice the wide as the next one because your minimum is always going to happen at phi naught. But this is the case if your junction actually, your transport looks like this. So you have a, you can think of your Cooper pair basically as going here, here, and coming back. So what you're picking up, the flux, your phase is only going to change by whatever flux is enclosed within this regime. So if you have a trajectory like this, then it's actually, you get what you expect from, you know, these textbook Fraunhofer. But if you have a diffusive junction, so if you have basically a very long diffusive junction, then your path, let's say your trajectories are all messed up. So each, you know, if you think about it, each Cooper pair, you know, when there are like a million different trajectories that a Cooper pairs can take because there's a lot of scattering, and this scattering means that there's different areas that you could basically enclose in your junction, and this is the, you end up with a, not a Fraunhofer pattern, you end up with a Gaussian decay. So the same thing actually would happen in single slit experiment if you have very rough edges there. So there, the wave fronts are gonna, they're not gonna have a nice uniform phase, they're gonna have all kinds of different phases. You're just gonna see if you have a rough slit, you're gonna get a Gaussian. Yes?
But this is from the EBIT paper, right?
Yeah.
So then you changed what here? How do you deposit the material? Is this a bad superconductor or something?
No, no, this is just a very diffusive junction. It's not bad. It's still a Josephson junction. You still make a SQUID with it, and it will work. But the interference pattern, it will give you a SQUID interference pattern. But a single junction, it actually
can be messed up.
Yeah. But actually, it doesn't affect the performance of the SQUID or so on. Yeah, because there the trajectory is not one junction;
Right,
it's two. Yeah. So there you get a beautiful SQUID pattern too. Right. Now you could also, with the same junction, for instance, this is one thing that might come in the talks. Even in the same junction, if your transport is split into separate channels, so for instance, in this case, you have a topological insulator where it's insulating everywhere except at the edges. So in this case, even though it's a single junction, you get a double-slit interference pattern, you get a SQUID pattern. And you could do a Fourier transform, you can actually do an inverse Fourier transform of the interference pattern to make a reconstruction of your supercurrent density profile. So here you see this is the Fraunhofer, and this is the SQUID pattern, but you could also get something in between. And so this way you can basically use the interference pattern to find out where the supercurrent is flowing in your junction. And we found a weird example of this in this superconductor ferromagnet hybrid here. It's a disc-shaped sample where, here I'll show you the example. This is even though there's one junction, it has this very distinct two-channel interference pattern. And where we do the, this Fourier analysis, we see that these channels always end up around, well, it depends on the material, but it's going to be somewhere around 80 nanometer. And it doesn't matter if it's like 1 micron or 10 micron, the channels are always going to happen at the edges. And we don't have a good explanation why this happens in this very simple system. And we actually had to come up with a new term. We had to call it rim currents, so people don't confuse it with edge currents, which comes out of a topology of your band structure. This is a very universal thing that only happens if you have triplet Cooper pairs and you put them in a curved geometry. It's been 5 years. We tried really hard to come up with something. We couldn't. And also know a lot of people who've tried, and we still don't know why this happens. So it's a very mysterious thing, but I can tell you about it if you want after the lecture. But okay, very quickly, I want to take 5 minutes to just tell you about different types of Josephson junctions according to the potential. Now, normally, as I said, SNS junction, SIS junctions, these are junctions where the intrinsic state, the ground state, is where your phase particle is at 0. So you see, the minimum here is going to be at 0. And that means there's also 0 supercurrent, because remember, the supercurrent across your junction is a function of sinusoidal of your phase. So if your phase is 0, if there's 0 phase difference, this is without applying any magnetic field, right? No magnetic field, just the intrinsic ground state of your Josephson junction is going to have a minimum at 0. This is 0. So this is a 0 junction, but you could also have a π-junction. So this is where your ground state is not at 0, it's at π. Now, how do you make a π-junction? Well, if you remember the superconductor ferromagnet hybrids, you remember the FFLO, you remember that there was because of the spin mixing, we were switching the sign of the wave function. So now if you go and, instead of, if this is the interface, if you stop the interface and put another superconductor here, what you've done is that you go left to right, you flip the sign of the wave function. You introduce the π phase shift in your wave function. So here to here, you have an offset of π. Clear? Good. Now, well, what does this mean for your Fraunhofer pattern? I'll let you figure that out for your homework, but remember, Josephson current is a sinusoidal function of phase. Sine of 0, 0. Sine of π, what is it? 0, yes. So these are just some examples of how you make for SFS junctions. I'm not going to go into that. But there is another way you could make it, and that is to use the pairing symmetry of an unconventional superconductor. So remember how I said cuprates, they have this D-wave pairing symmetry, and this D-wave symmetry is basically locked into the axis of your crystal, right? So if you, for instance, here what you have is the film of cuprates grown at 2 different orientation, because the substrate actually flips its orientation from one side to the other. So now this is a D-wave superconductor and this is a D-wave superconductor, but they meet at a certain angle. And these are, let's say, 3 different scenarios. This is one case, this is the other one, this is the other one. Now, which one of these do you think is going to give us a π? This one, which one of these is going to be a π-junction? Just look at the colors. It's not that hard. Who says D? Okay. What about E? F? Okay. Well, the correct answer was actually D. Because what you're doing, you just think about where you're going. As I said, you know, in the D waves, what you're doing is that this part of your K space, or in this case, real crystal space, and this part are out of phase by exactly pi, right? So now, think about these two. This is actually, if you go and drill a hole here, you make a squid. So here you see you're going connecting the white part to the white part, but now you're going connecting the dark part to the white part. Now what you have is a phase of pi. While in this case, you're basically just connecting the same facets of the same phase with each other, so you get 0 and 0. And this is the interference pattern of these two squids. Can you tell me which one is the 0 pi squid and which one is the 0 squid? The upper one is the pi. Yes, because that one, you see, both for positive and negative current, your critical current is suppressed. Why? Because there's a pi phase shift there. And remember when we talked about little parks? Well, I mentioned that it's like being halfway between 0 and phi naught. It's like a half phi naught. This is the place where your critical current needs to go maximum. You have actually, you know, remember the phase needs to wind by multiples of 2 pi. And now if you put a pi phase offset in there, it has to, your supercurrent needs to do the other pi. It needs to compensate for that by having a current. So if you have a current through your system, there's a lot of supercurrent, that means your cup is full, so you have minimum supercurrent. You have minimum critical current at 0 field. That's what it means. Whereas in the other case, it's the reverse. This is a final example. Basically, you could also get interference patterns that look like this. What on earth is going on here? Well, this is, I'll show you what. This is basically what happens when you have a cuprate superconductor where the crystal facet has these zigzag jagged edges, and then you connect on the other side niobium, some S-wave superconductor. So in this case, you get a zigzag junction where, you know, there's different facets. Remember, there's a phase offset of pi between this facet and that facet, and there's a phase offset of pi again between these two facets, right? But you're connecting these different phases with a S-wave superconductor which doesn't have any phase variation, right? Can you guess why now the supercurrent is suppressed around 0? Why you have maxima at finite fields? So when your supercurrent is minimum, what does that mean? There is a, think about a cup. It's full. So your cup is full. Why would it be full?
If you go that way, you have plus plus, and if you go that way, you have plus minus, so if you put pi 0.
Because you're on the right track, yes, because when you have an array of actual vortices trapped on this zigzag. So this is another experiment where they image these vortices. So you see here, and this edge, at this corner, you go here to here, there's a π-junction. And that means there's a loop there's a superconducting loop. So there's a spontaneous built-in currents running here, here, here. And these are the vortices that they image with the scanning squid. So you get an array of vortices at 0 field because of this phase shifts that you have between the cuprate and the S-wave superconductor. So there's a lot of supercurrent here, there's one here, there's one here. Now, can anybody tell me what this flux of these vortices is? Is it 1 phi naught? Is it are they just normal abrikosa vortices? So what is the flux that this squid is measuring? It's half, exactly. Why half? Because a full vortex, only the orbital phase of your Cooper purse couples to the external field. if you have a π-junction, that's like cheating. You're pushing your Cooper pairs already by pi, so then the orbital phase needs to wind by pi, so then it does half the work, so you get half quantum vortices. So you get an array of half quantum vortices basically here, and they're flooding your system. Now what you do is that you apply some field, and as you apply the field, it starts to compensate for these vortices. And that's where, so your vortices kind of go away, because that pi phase shift that was introduced by the zigzag, by this π-junction, are now compensated by the field, and therefore you recover your maximum critical current. Therefore you empty your cup, and then you could have maxima. And you could also make it with the array of 0 π-junction using SFS junction. But final thing is actually, there's two other classes that are more exotic. That is a so-called φ-junction or φ-naught junction. And here, if you look at them, these are junctions where the ground state, actually, it's neither 0 nor pi. It's a phi. And what does that mean for your Josephson current? If you remember, this was a sine phi, so if it's not 0 or pi, what does that mean? You have a current. Yeah. This is basically, it shows you spontaneous time reversal symmetry breaking, and you can call this a phase battery. So this is a system where its ground state has a current, an actual, not a superposition current, an actual current that's going through your system. So just, you know, in analogy with the battery, which provides a constant voltage that drives the current, here, this junction, you know, supplies a constant phase offset that gives you a constant current. So it's a system where it's in its ground state, you have currents, you have kinetic energy. And you could do this by breaking the symmetries carefully. And this is actually one of the projects that Fabian, who was a master's student actually from last year, wanted to make this device this year. So this is, unfortunately, I don't have time to go through it, but there are ways that you can actually create this φ-naught junction, these phase batteries, using, you know, by creating spin imbalance and other things in this system. So this is a device he made. I'll tell you about it maybe, I don't know, maybe some other time. Unfortunately, we're already way over time. Okay.